We are now in a position to present the final algorithm. So the algorithm uses a ballot leader election that we described in the previous lecture, and it uses a FIFO perfect point-to-point links. The algorithm, the Sequence Paxos algorithm itself, works in the asynchronous system model, but it requires the ballot-based leader election, which will satisfy its properties only in the partially synchronous model. So what we are going to do here is to summarize what you already know. And the algorithm, as we have already described earlier, will fit in 2 slides. Only 2 slides to describe the whole algorithm with no abbreviation. So the first slide now is just to remind you with the state of replicas in Sequence Paxos. I am going to go quickly through this because all what you're going to see, you have seen before. So we have the sequence of proposed commands coming from the clients. We have the length of the longest accepted sequence per acceptor used to make decisions. And we have the length of the longest decided sequence per acceptor used in the prepare phase to collect knowledge about the acceptor's decided sequence. And we have the length of the longest chosen sequence, which tells you when should we actually decide. Then, before we're using a set S, when we are collecting promises from the replicas at the prepare phase. Now we make it more concrete. We don't use sets. We just use an array here. And this will be promise X per acceptor. So it is initially for each acceptor, it is undefined. And it goes so that for each acceptor, we give the round number and the sequence. And this sequence will be used to select the adopted sequence, of course, if you remember that. Then we have the replicas, including acceptors and learners. So NL will be the leader's current number, initially 0, and the leader is initially unknown. And the state, we have the following state. We have either you are a leader or a follower. And if you are a follower or a leader, you can be in the prepare state or in the accept state, and the follower is initially just a follower, did not arrive to the prepare yet. And here is the promise not to accept in lower rounds, and here is the round number in which a value is accepted, the latest round number. Here is the accepted sequence. This is really sometimes called the log, and here is an index, which is a prefix of the log that we know it is decided. So we go step by step, but quickly this time. When a replica gets an indication of a leader, then it checks if it is the leader or not. If n is greater than the current leader, then it changes the leader. That is fine, and this will be our round that we're going to work on. If I am L, then I am the leader, and also the round is greater than the promise, I can act as a leader. Otherwise, I'm a follower. And you can see what happens. I mean, this is like initialization. Set of proposed command is empty. The longest accepted sequence is initialized. And this really used to collect promises from the replicas when you are a leader and you know the length of the decided sequence at each replica. The acknowledgement is used to collect a majority of promises. We know the length of the longest sequence. Then we send a prepare message to everybody except myself. We add the suffix of the accepted sequence at the index of the decided sequence and the round number to this set. And we say now we know about the length of our decided sequence as a leader, and I set my promise to be NL. Okay, so that is how the leader does. So leader now is in the prepare phase, and he sent a prepare to all other replicas, and if they get the prepare and accepted because of this condition, then they move to become a follower in the prepare phase, and they send their suffix and the decided sequence. We have seen that before in a promise. So the leader now is in leader prepare phase. So if that is the case and the leader is in prepare phase and he's getting a promise, so he adds the pair NA and the suffix to the set of acknowledgement. He now knows about the decided sequence at that replica A, and then this is a set from where I received promises, and if that set is a majority, I pick the max, then I know how to augment my sequence. I take the prefix until it is decided, I take the suffix and I add any commands, and now I have constructed my log, which is VA. And I say now, this is the length of my accepted sequence. I initialize the sequence of proposed command and I move to a leader accept phase. Now I have got promises from a majority. And I send to those which I got promises, I send them the information that they don't have in what we call an accept sync message. For late replicas that send a promise while the leader is in the accept phase, I in fact update what I know about that replica and I send an accept sync similar to the one above, and here just send him also information about what is decided so far. This is an optimization if there are new commands are coming, and I let you think why it is an optimization if there are more commands, because what is this is saying, it's just telling where in the replica's VA, the log, where I can move the index of what is decided further in the front. So when the leader gets a propose and he is in the prepare phase, he just accumulate them. And when the leader gets a propose while he is in the accept phase, he just augment his sequence, augment the length of his sequence, and then send to all the processes that he knows of. Until now, the ones that got promises, we send an accept, so that is clear. The accept sync, this is the one that goes to the replicas and sent from the leader at the prepare phase. So if I'm still in the prepare phase, this is very important, then I do something. I check that this is the current leader in my round. I update the round of accepted things, and then I take this information and augment it or extend my sequence with that information after the so-called decided sequence, and I send accepted and I move to the accept phase. In the accept phase, as we said, replicas get accept message incrementally, and that's what they do. They get an accept message, and if the leader is still the current leader, they augment its accepted sequence and send an acknowledgement, which is accepted. When I get a majority as a leader of accepted messages, I check if I have new chosen sequence, a sequence that I have collected a majority for, and if so, and it is new, then I send a decide to all the processes that I got a promise from. And this is a decide which we have seen in the last unit. So this is the algorithm. Actually, it is not that difficult. It's just 2 pages, and it is a complete algorithm that works in the asynchronous system model with arbitrary delays. Now, what we have developed at this point is a complete, and in my view, simple and efficient sequence Paxos in the fail-silent model, which can create a consistent replicated log, and that log is VA at each replica. The algorithm guarantees safety property of the sequence consensus as long as the following assumption holds: FIFO perfect link, and an eventual leader abstraction that guarantees for any indication response this combination is unique and is monotonically increasing. The same requirement as in single value Paxos. Most of the time, when a command is delivered to the leader, a round trip is needed for deciding on C, and also commands are pipelined in the network. For liveness or progress, the leader election should satisfy that. For any process P, if P is elected as a leader, then for any previous event and process Q, N is greater than N prime. And we get liveness if a leader is staying and considered a leader by a majority of processes for a sufficient amount of time before being overtaken by a higher number process. This is basically saying that the network is stable for some period of time. Otherwise, no requirement, again, on strong accuracy on the leader election algorithm. This is the requirement that we have. We have finished this lecture. In the next lecture, we are going to see what can we do when we want to weaken our condition on the system. For example, what would we do if we have a session-based FIFO link, which means that some messages that is a suffix in a FIFO link could be dropped. The other aspect is what can we do to provide a fair recovery model where processes can, in principle, stop running for a while and come back again. What is the data that we should have in a persistent store that the algorithm should still work fine? And you will see that it is very minor modification we need to do. From there on, we are going to move slowly to describe the difference between this algorithm and the raft algorithm, the known raft algorithm for replicated log. And we will see that it's just different choice strategies that has been taken in raft. And this we will describe them and describe their correctness. See you in the next lecture.